Station keeping behaviour for stratospheric balloons entails maintaining horizontal positioning within the radius of a target base station. Initially, station keeping was proposed for communication relay between base stations and other balloons. However, it has also been shown to be helpful in other areas, such as long-term, non-intrusive wildlife surveillance and atmospheric analysis. However, the nonlinear relationship between the control actions and control signals, i.e. distance to the radius, along with the low horizontal control authority, makes station keeping a difficult task to solve. Researchers have investigated station keeping control within state-of-the-art controllers trained using reinforcement learning and geometric planning. However, reward hacking, experienced when training reinforcement learning-based controllers, can lead to unintended consequences. Specifically, within the context of our work, we can show how the agent can learn risky behaviours which can lead to worse results and impact the optimal launch location. Researchers have also invested stochastic system modelling with Monte Carlo ensembles of real wind data to predict flight trajectory and the landing site. But, to our knowledge, no one has investigated the optimal placement of stratospheric balloons to optimally complete station keeping tasks. We illustrate here that the optimal placement is a dominant component in determining the controller's success due to the time-varying wind fields for which the horizontal displacement is wholly dependent on. Evaluating the performance for an initial state is costly due to high-fidelity models, and additionally, regulators mandate providing the launch location in advance of flights. And delaying this decision allows for access to more accurate weather predictions, but also reduces the time available for the optimizer to determine the optimal launch site. Our research here investigates how we can find an optimal solution in fewer steps due to the time budget and computational cost. We aim to find the optimal placement of the balloon by selecting the best longitudinal and latitudinal and time offset. We optimize the cumulative reward obtained by running a full trajectory controlled by our soft actor critic policy. The process is constrained by the size of the environment, which is roughly 400 kilometers by 400 kilometers, and a maximum time offset window of 24 hours. The reward function here maximizes the agent's proximity to the target at each decision state. We also investigate an alternative form of the reward function used in the state-of-the-art to demonstrate how an agent can exploit the reward function and lead to poorer performance and unseen data, which impacts the choice of launch sites. Regarding the system dynamics, we use the equations of motion of a latex balloon outlined in previous works. In short, balloons are influenced by buoyancy, drag, and weight forces. The highly stretchable polymer used for latex envelopes expand as they ascend, maintaining very small pressure differences. And due to the low overpressure, the buoyant lift remains roughly constant with altitude and will rupture before reaching neutral buoyancy. The balloon system is underactuated, where control is only available through the ascent rate by venting lifting gas and dropping mass, and drag acts to move the balloon horizontally. We use the 5th generation ECMWF European Centre of Medium Wind Forecasts reanalysis wind dataset between the dates of the 1st of November 2022 till the 28th of February 2023 in intervals of 6 hours at a resolution of 0.4 degrees at longitude minus 130 degrees and latitude 1 degree. The same geographical location within this time window ensures consistent seasonal and positional wind variations, and the data is split with the first portion of wind data used to train the reinforcement learning policy and the second half to evaluate over. We use a soft actor critic policy to control the balloon, where the actor and critic are parameterized by a neural network. The policy aims to minimize the simplified KI divergence, and the critic is trained to minimize the mean squared error between the predicted and target action values, where the predicted action value incorporates policy entropy to ensure or enable exploration. As mentioned before, the balloon is underactuated and can only control the ascent rate by dropping mass and venting lifting gas. The action space reflects this by decomposing the desired ascent rate into 3 actions: altitude, time to reach, and if to float. The state space consists of a combination of measurement system and wind states. To evaluate the extent of reward hacking, we augment the reward function used in previous work with a tanh function to add further weighting to the central target region. This is in comparison with previous works using a flat 1 reward inside the center. We sample uniformly across the horizontal plane, keeping the same sampled launch locations for both reward functions. And to compare, we evaluate both functions with the total number of steps inside the region for each trajectory and the number of trajectories that reach the region. We make use of Bayesian optimization with a Gaussian process surrogate function to optimize the launch site of the balloon. The Gaussian process is parameterized with a mean function of 0 and a 5-2 Matern kernel. Furthermore, we make use of the expected improvement acquisition function, which maximizes the high expected improvement over the current best observed value. To achieve the target value, we run a full episode and collect the total reward. Each newly collected sample point is added to a collection, and the Gaussian process is updated by maximizing the marginal log likelihood, and this process is repeated until the maximum number of sample points is reached. The availability of wind currents across the altitude layers, as indicated by the size of the wind cone, has a direct effect on the station keeping performance. The wind cone here represents the variety of wind current directions across the altitude layers. They provide evidence for the temporal performance across the dates, as can be seen here by the month of November. After evaluating 2 policies, trained using the 2 different reward functions, we find the augmented reward function generalizes better for unseen data. The augmented reward function we proposed reaches the center more often, and furthermore, the ratio of trajectories that reach the region is higher. For further analysis, we compute the kernel density plot for each transition's distance to the center over all trajectories, and we find the shift in density is smaller for our augmented function. And to explain the shift, we show the policy trained on the non-augmented reward function exploits the geometries of the target region by flying across the circumference. This leads to risky behaviours in unseen wind data, which pushes the balloon outside the target region more often than the augmented reward function we here propose. We compare our proposed Bayesian optimization approach against the particle swarm optimization and uniform sampling of the space. We find all methods sufficiently find, on average, roughly the same maximum value over the test dataset. However, Bayesian optimization converges in nearly half the number of steps compared to particle swarm optimization. Our augmented reward function is able to achieve a greater maximum reward compared to the non-augmented reward function. And finally, by analyzing the optimal positions found by the optimization algorithms, we find that PSO and BO identify very similar launch sites. Thank you for listening.